Today's webinar will be presented by Luis Zaganel, an associate professor at the University of Campinas in Brazil. But before we begin, I'd like to thank our sponsor for the webinar, RHK Technology. With that introduction, off to you, Luis.
Introduction. Thank you for the introduction, Mark. It's a pleasure to be here. And I'd like to begin by mentioning that the morphological and electronical properties that we will be interested in will be studied by scanning tunneling microscope. But it's a very versatile tool, so I'll start by describing a little bit about it. And the optical properties that are interesting for us are the luminescence properties of these 2D materials that we are going to explore in this presentation. So with that, I would like to start by acknowledging also that the work that I'm going to present here was performed by several students that work in my group. So this is a group picture. And also that we have used a lot of help from our collaborators. So here's a small list. And with that, I'd like to start saying a little words about the tunneling microscopy for those that are not familiar with it. The basic idea of tunneling is that when you approach two metals and you have a dielectric object between them, like vacuum, from the quantum mechanical perspective, you are approaching two wave functions as the one that I'm showing on the right-hand side of the slide. And the idea is that when they are sufficiently close together and if you apply also a voltage, you can start to observe a current. And if you make all the modeling about this, you can see that the current depends on the density of states on the, one of the electrodes that we're going to call the tip in the STM, and the density of states on your sample. And also there is a matrix transfer that tells how one relates to the other. And there is an interesting approximation that when you divide the current by the voltage, you end up with some assumptions to have only the density of states of the sample. So that's a direct tool to study both the occupied and unoccupied states on the sample. And people like to make this diagram that I show on the right-hand side, in which we have the density of states on the tip, one of these electrodes. And if you choose dry tip, is supposed to be fairly constant, close to the Fermi level. And then you have a different probability to tunnel into the sample, depending on the density of states of the sample, regardless of if these states are occupied or if they're empty. And to make a microscope with this, nothing can be more simple. Of course, there are plenty of details, but you can shape one of these electrodes to be a very sharp tip, ideally only with one electron at its, one atom at its apex. And by moving this tip around, you can start to make images. So the idea is always that you have a metallic tip, sample that you want to study, apply a voltage and measure a current. So this was developed in the 80s, and it was the first way, the first results which have been possible to see atoms in the real space. And one important aspect is that you have a system that changes the tip to sample distance, so you can get the tip closer to the surface or farther away from the surface. And the distance between tip and sample is very, very, very small, so close to 1 nanometer. And by moving the tip left and right and adjusting its height, controlling the current, you can start to make images. And for this impressive result of seeing atoms in real space, these authors got a Nobel Prize in '86. And how this system looks like. So although you can see atoms, I'll show some images on the next slide. The microscope is very small. So here you can see the microscope that we have used. So it's in air outside the ultra high vacuum where it usually is. And you see that it is, and this is very small, so it's smaller than a teacup. So it's not one of those big, huge microscopes that sometimes are used to see atoms by other techniques. And to show you just 2 images where you can see some atoms. So these are images of the same structure. So the one on the right is the original image that was published in the PRL in '83. By the creators of the STM. And the one on the left-hand side is one that was acquired in our group. So it's a very standard image of the silicon 111 on the 7x7 reconstruction. And each of these red dots is one atom. And you see that, of course, it's much easier and we can make it much more beautiful and good looking now than it was before, but basically the same image, the same structure. You can see this triangular structure here and here. So after just very brief introduction, it is interesting to mention that an STM is a great tool because we have like very high spatial resolution. We can see atoms. There are plenty of examples where this technique is able to see atoms and to reach atomic resolution. I didn't show any example, but that's also very usual to apply this technique to make electron spectroscopy. So we can see the local density of states. You can measure the band gap of the sample, but something is missing. A key element is missing. And this, the main thing about this webinar is that we can add optical spectroscopy. And for that, we need to add some optical devices onto the STM. And to add optical capabilities on the STM to be able to study morphological, electronic, and optical properties on the same sample is something that has been done already in the past. That's not really new. But that was typically done either by adding an optical fiber close to the tunnel junction, but optical fibers are good, but their numerical aperture is in general very small. Either by adding some lenses, but then again, if you are obliged to put the lens on the side, you're very limited in the amount of light you can collect. And some other geometries, people have tried to use some kind of on-axis mirrors, but they impose several restrictions on the instrument itself. You can imagine that in the case of this case here, the whole mechanism for moving the tip is on the light path, so you can lose a lot of light. And the thing that we have developed and applied very successfully is an off-axis parabolical mirror, so you can see it here. And it's off-axis because the light goes to the side, so it goes parallel to the plane of the sample and not axial with the tip. And in these schematics here, you see basically the whole setup. So we have bias that's applied to the sample. We have the tip that goes through a small hole through the mirror, and the tip is connected to the current preamplifier, and this goes to the control system. And we apply voltage to the 3 piezo's that control the height and the lateral positioning of the tip to make images, of course. But when the tip is in close range, so we have tunneling, or we are somehow adding electrons to the sample, and the sample is suitable, is optically active, so direct band gap and things like that. The light is so generated, and this mirror can have a very high numerical aperture. So we have about 70% of collection efficiency, and this light is directed to the outside of the UHV chamber, and we can do several things with this light, with this optical access. One of them is, of course, to send this light directly to a spectrometer, so we can record and study the light emitted by the sample. That's one of the main topics on this presentation. And we can also, on that small optical table that I have just shown you, inject light with a laser and record photoluminescence or Raman spectroscopy from the sample that is sitting in UHV. So you can think about samples that were prepared in situ, like small molecules that cannot be observed easily in air. But regardless if you're doing one or the other, the interesting thing is that we have a high numerical aperture that increases a lot the amount of signal, and you can have very, very tight focusing because of the large numerical aperture that this focusing element sustains. And we have recently published a paper describing this device. The core ideas are rather simple. It's a parabolic mirror that is mounted on a manipulator that is inside the UHV, and there is a viewport so that the light goes to the outside. And here I show a picture of this device and a picture of the mirror, the small hole that you see here, and the tip goes through it and reaches the sample. Of course, there are plenty of details. Some of these details are covered in this scientific instruments paper, review of scientific instruments. And of course, there are plenty of other technical details that are not the point here today. So entering on the topic of 2D material, so I just described you a little bit about how we are going to study these materials, but now I'd like to mention a little bit of why the optical properties of these materials are important. One of the reasons why these properties are important is that you can find a suitable 2D material to cover whichever wavelength you're interested in. So there are plenty of materials that have this layered structure. You can come from graphene, which is very well known, to black phosphorus, to several others. And each of them is going to emit light in one specific wavelength or has its electronic properties linked to optical properties in a specific wavelength. So it's very versatile. And the other reason is that in general, to make optical devices, you really need to think a lot about the heterostructure that you want. Because if you want to establish PN junctions, or if you want to have a substrate and grow your material on top, and if you want to have contacts and everything to make a device, in general, you are very restricted about the choice of material, because you cannot grow one material on any other. You have to think about the lattice mismatch and everything that MBE has taught us through the years. But on van der Waals heterostructures, there is a different story, because in this case, since the connections outside the plane are not very relevant, you can really stack materials of totally different lattice parameters, and they still can function, and you can even grow one material on the other, even if the lattice parameter is not matching, and you can do that with very low defect density and with very high quality, with optical quality. So that's why many groups are investing a lot in studying heterostructures that are composed of tungsten selenide, molybdenum disulfide, or hexagonal boron nitride, and graphene, because you can think about conducting to make the contact. You can think about some isolating layers to have your device function the way you want them to function. And you can just stack this and it's supposed to work, right? And in the case of the tungsten selenides or these transition metal dechalcogenides, it's very interesting because they're known for several years. So many people have studied them many years ago, but recently, 12 years ago, people discovered that when thinned to one monolayer, they become a direct band gap. And this is very interesting because you have a new and an interesting material as a direct band gap. And that's the kind of material that is really needed when you want to make an optically active device like LED or something like that. And depending on the TMD that you are using, see here I show 4, which are the main TMDs for luminescence. And you see that each one emits light in a different wavelength, and they also have different properties if they are mechanically transferred into silicon oxide or if they're kept with hexagonal boron nitride. So there is plenty of interesting things to be studied in these materials, which are, so to say, a promise for next generation of flexible LEDs, for instance. And there are plenty of interesting things to learn from this. So here I'd like to show you just another 2 examples from the literature before starting my own results. In this case, it's STM images, and you can see some dark and bright regions in this surface. And if you do this density of states measurement that I was just mentioning, you can see that one of these, but they also link to a metal vacancy. So when, for some reason, the metal is absent, so there's a defect in which the metal is absent, you see a state, and it's doping the sample with a hole, and if the chalcogen is missing, you see that it's doping the sample with electrons in this case. So it's interesting to see that, as in other semiconductors, defects can be used to tailor electronic properties, and we can use the STM to see the defect density, for instance, and to see the impact that each defect has on the electronic properties of the material. And this kind of defect, if you think about the optical properties, have a huge impact on the luminescence of this material. So here in this other study, I show that an individual defect that is seen here on the luminescence map or seen here is shown to be an extremely narrow emitter, and also to present this so-called anti-bunching, which is a signature of single electron, a single photon emitter, which is associated to the presence of a 2-level system, which most likely is linked to one individual defect, an atomic defect. So you see that just removing one single atom from TMD, in this case is tungsten selenide, you can create a single photon source, which has several interesting applications in technology as well. So in the study that we have conducted, we also looked at tungsten selenide. So here I show you optical microscopy image. This region is a monolayer, so we have here possibly a bilayer, and here a much thicker region. And we start to make standard characterization. So we have done AFM, and we see the step height, which is higher than we expected for a monolayer, but I'll explain why in a minute. We have entered on the STM and make a small annealing to make it clean for imaging, and have seen a huge density, or a significantly high density of these dark defects. And this sample was nominally p-doped, and referring to the literature, we could see then that this p-doped is linked to the metallic vacancies, and that's what we saw, a lot of these darkish defects for positive bias. And by performing STS, we saw that the Fermi level is indeed very close to the valence band, and this is then again a signature of p-doping. So we see that the electronic properties and the morphological properties are closely related, so we can understand one with the other. And this also explains a little bit why this sample in bulk form even is a p-doped semiconductor. But then we try to look at the luminescence of this sample inside UHV, and we had a very hard time getting it to emit light, and we try to understand why. And we observed that before making this annealing in UHV to clean the sample for the STM, it was emitting light very well. So before annealing, we saw this photoluminescence emission, and after we saw this. So we lost basically all the light that it was emitting, and we also saw on the Raman spectra the signature that the sample is in fact a monolayer, which is the 2LAM peak on the Raman spectrum. But after we also lost that peak, which is the blue curve. And we went to compare this with a new round of AFM imaging, and we observed that before annealing we had a step height, which is, as I said, much higher than we expected for the monolayer of the TMD. But after we got something that is much closer to the expected. So our interpretation for this, and this is really well discussed in the literature, there are several examples mentioning this, is because when we make the transfer in air from the TMD into hydrophilic surface, there is always a layer of water that is trapped between the TMD and the gold support. And this water just remains there until we make some annealing to remove it. And so the point is that the TMD was decoupled from the gold, and this is very important because the gold is known to quench the luminescence from this from TMDs because it creates a lot of non-radiative recombination channels at the interface between the gold and the TMD, and we should always remember that like the sample is just 3 atoms thick, so any state that the gold creates that enters the TMD could create so this non-radiative recombination channels. So given this, we went back to the STM and said, okay, of course we can do STM in UHV, but there's no reason why we cannot make it in air. So we simply vented our STM and did some other things to make it better. But we could then have photoluminescence, that is the black curve that I'm showing here, from this sample, this TMD on top of this gold support or substrate. And also, which is the interesting part, the the luminescence induced by the tunneling current, which is the blue curve here. And there are several reasons why this is interesting, but one of them is that we are really trying to look at the sample from an electronic perspective. Like, we know that in photoluminescence we create an electron-hole pair, but here we're just injecting electrons and trying to get luminescence out of it. And of course, the first thing that one has to think about is that the luminescence that we see could be a cavity mode, a plasmonic cavity mode, because we have like a metallic tip and a gold support. So the first thing that we do is just to change the sample bias and to see that the sample is always emitting light at basically the same wavelength. And this is a proof that it's not a plasmonic emission, it's really excitonic. And we can also see other aspects, like the sample is not emitting light when we have a negative bias, which is interesting because we must therefore inject the electrons. And we know that sample is p-doped, so it makes sense because we have we must have both carriers to generate light emission. And we also have no light emission if the sample bias is below 2 volts, because 2 volts is the electronic band gap of the TMD, or of tungsten diselenide. And it means that we really must inject a carrier, an electron, on the conduction band. If we try to inject it somewhere else, or on the valence band, for instance, or to remove an electron from the valence band, or to try to inject an electron intragap, we just saw no luminescence. And there's another aspect that was interesting to be observed in this system, is that we could study a little bit of the dynamics, because if you have very low current, like in this case, the luminescence spectra is very similar to the one we observed in photoluminescence. So it's dominated by neutral exciton emission, which is A0 here, neutral excitons. So that means in our interpretation that we are injecting one electron and it's looking for a hole to recombine, and that's fine. But it can happen that this exciton meets another carrier and they combine to form a trion. And this is the other peak here. And if you're doing photoluminescence, so you create the pair, so the doping of the sample, or the extra carriers the sample has, can have a little effect. But if we're injecting only one carrier and we are injecting a lot of it, and that's the point of increasing the current here, up to significantly very high currents, we see that the trion emission starts to dominate, which means that we are injecting one electron, and before it even finds a hole, or just after it finds a hole, we are injecting another electron, and that forms a trion, because there is insufficient amount of holes to recombine with the amount of electrons that we are injecting. And we can see this here, that from this spectrum, we see that there is a linear combination between, a linear relation between the tunneling current and the area ratio between the trion and the exciton. So we can learn something about it. And another aspect that interested us is what's the effect of the electric field, because the region that it's emitting light is subjected to a very high electric field under the tip. And we basically saw no real influence on the peak position. We saw on the ratio between the trion and the exciton peaks, but on the peak area, but not on the peak position. So the peak position is basically the same for photoluminescence and for tunneling current-induced luminescence, for whatever current and for whatever voltage. So for us, this is an indication that we are really observing a property of the sample and not a property of the sample subjected to a high intense electric field. And one last aspect that we observe in this sample is that an STM is always also an AFM, meaning that if you push the tunneling conditions a little bit too far, the tip really starts to exerting some force onto the sample. And we could use this to press a little bit the TMD and get rid of the water. So the water would go to the sides. This is also well documented in graphene on a scene from AFM. So you can manipulate this amount of water that is beneath your two-dimensional material. And by doing this, we could see that on the first round, we have only the excitonic emission that is here. So we understand that the TMD is decoupled by the water layer. And if we insist for some time on the same region, we start to have both emissions and in the end, just the plasmonic emission. So you see here how the plasmonic spectrum in this system looks like. Is really nothing to do with the excitonic emission. And you see that if the sample collapsed, in a sense, it's totally linked, ruggedly linked to the gold support, not only we lose the excitonic emission or its quantum efficiency gets too low to be observed, and at the same time, we start to see this cavity mode, the plasmonic mode of the tip gold support junction. And to sum up this part, we just proposed a little model to say that we should inject the carriers into the conduction band of the TMD, that it would recombine, creating an electron hole pair, an exciton, and then decay emitting light, and this extra charge should go to the gold support by means of by tunneling through the water layer. So the water layer is really necessary to decouple them and assist this process. So that's basically the interpretation that our data suggests. And moving on to the other 3D material that I would like to explore, that's hexagonal boron nitride. It's a very interesting material also. It's being studied for many years, and there are plenty of interesting things that is teaching us. And one very interesting aspect is that hexagonal boron nitride is a very bright emitter. It's very, very bright in terms of quantum efficiency. And for many years, people thought that this is because there's a direct band gap, but since the gap is so high, so it's close to 6 to 7 to 8, depend on the model, it's very hard to measure the band gap. And recently, it was possible to show that it is in fact an indirect band gap in bulk form, which means that there must be some other reason for it to be such a bright emitter, even at ambient temperature. Moreover, when in a monolayer, it has been shown that it becomes a direct band gap, similarly to these other 2D materials that we have just discussed. So you see, from the physical point of view, there are interesting aspects to explore in this material. And for the application point of view, it's interesting to consider that the hexagonal boron nitride has potential to be made into a far UV LED or far UV emitting device that could emit light close to 6 electron volts. And this could be interesting, like to clean surfaces, just for the purpose of getting them rid of virus and other things that you can effectively inactivate by means of UV light. And some other interesting aspect is that since the band gap of HBN is so high, as other high band gap materials, it can host interesting defects. And there is a defect that has been observed but in this study, for instance, that is emitting light basically at 4.1 electron volts. and it is as well a system that has this anti-bunching property, and because of this, you know that it's emitting individual photons, so one photon at a time. And this is then again interesting because HBN is a very good light emitter at room temperature, and if it's emitting single photons at room temperature, you can think about making devices electronic devices that would emit a single photon on demand, and there are plenty of industrial applications on cryptography or quantum computing that could use this device. This single photon device operating at room temperature and emitting electrons, emitting photons on demand. But there's still some open questions about which exactly is the kind of defect and how can we better explore and control this. And for this study, we explored a sample that was made of HBN monolayers that were actually grown on hexagon on highly oriented pyrolytic graphite. So basically is HBN on HOPG system, so boron nitride monolayers on graphite. And it's an interesting system because then again, it's a van der Waals structure, and you would expect that the layer beneath, so the graphene layer beneath, is not going to impose several problems to the HBN layer on top. And here I show you the schematics of the sample on the left-hand side, and some AFM images on the right-hand side, in which you see the HBN that's basically covering everything, and it's a little bit thicker or deorganized on the grain boundaries of the HOPG. And there's also some small windows in which you can see the HOPG where HBN didn't grow, so you can control the growth time and have this kind of partially covered. And it's also a self-terminated growth process, so it's supposed to have just one monolayer in most of the area. So we go to the STM with this sample, and the first thing that we saw that is basically defect-free. It's very hard to find defective regions on this sample, so it's hard in a sense just by looking at the image or to the morphological aspect to see which material are we looking at. So we need to go to the electronic properties, so making STS. And we observe that in some cases we managed to see the HOPG, so we managed to find some of these windows, and in the vast majority of the sample regions, we had a large band gap, and we are therefore on the HBN monolayer. And we could also see that in some regions we could observe this kind of imaging, which is a Moiré pattern, which means that since the epitaxy is not perfect, the HBN decided to rotate a little bit on top of the HOPG to accommodate itself. So that's also something that is very usual when you have a van der Waals structure, that there is some interaction between these layers, and there is sometimes a rotation and sometimes some kind of interaction between them such that it accommodates somehow. Well, the first thing that we want to do, looking at the sample, was to get its electronic property. So we want to measure the band gap because it was not very well known. And it's a kind of a challenge because the band gap is really high, but it's a kind of challenge that STM is really suitable for because there is no problem to go to high voltages there, as it's a problem to get a 10 electron volt laser, for instance. And we did it very, very carefully, and we had the assistance that the HBN provides very beautiful looking STS curves in which it's very clear to see the conduction band minimum, the valence band maximum, so they're beautifully shown. And we have a very good statistics. So we had studied like 480 STM curves. And we could see that if we use the current a little bit too high or a little bit too low, we start to see problems about statistics or about interaction with the HOPG underneath. But there's a large current range in which everything works perfect. And it was in this range that we acquired these curves. And we could see this 6.8 electron volt gap. We also, of course, try to see the excitonic light emission in our system, but it was very, very hard to get it. And one of the reasons is that it's not that straightforward to have optics adapted to that range, to the DUV range of light, but that's something that we are working on. And to get the luminescence of the sample, we count with the assistance of collaborators that performed DUV photoluminescence and could measure this luminescence peak to show that the sample has 6.1 band-to-band excitonic transmission of 6.1, even not band-to-band, sorry. And that's interesting because we could, with the band gap 6.8 and the optical band gap or the excitonic emission 6.1, we can do the math and see that the excitonic binding energy is 0.7 electron volts. And that's huge, is extremely high, orders of magnitude higher than the 3-5 semiconductors excitonic binding energy. And this explains why the sample is so optically active, even at ambient temperature. That was something that was really expected, but no one until this study had measured this for monolayers and could see that this was the excitonic binding energy. And that's interesting because it's possible now to compare with models and to evolve the models that are also studying this material. But of course, featureless sample is boring, so we try to find some defective region. And of course, there is a huge source of carbon beneath the HOBN, and we could expect that in some regions, at least, there should be some carbon-related defects. And we saw this region in which there are plenty of these small points. Some are individual, some we see as sort of twins. And if we take the profile here, we see that they are quite large, but that's very usual that even if you remove a single atom of one of these 2D materials, it creates a larger, much larger impact on the electronic properties. And then again, when we look at an STM image, we are looking at electronic properties and how they distribute, because this is local density of states map in a sense. And we could also make STS spectroscopy and see that this kind of defect have a state close to the valence band, close to -2 electron volts, which is then again interesting to start to study these defects. And of course, we aim to get atomic resolution images of these defects and better STS. And it's really a very good start. And regarding the optical properties, even if you could not see the luminescence at very high energies, we could see photoluminescence close to the 2.1 emission. So doing photoluminescence, that's what was observed, this spectrum here, so at room temperature and at liquid nitrogen temperatures. And we see some Raman peaks linked to the HOPG and this luminescence spectra, that is also associated to carbon defects close to 2.1 electron volts. And you could not see some excitation of these defects due to the tunneling current, but we could do cathodoluminescence, and it's a different approach of using this setup, but it's very straightforward. We can just retract the tip, so we take it away from the sample outside the tunneling condition, and we apply to the tip a higher voltage, like 160 volts in this case. And then this tip starts to emit free electrons into the vacuum, and these electrons accelerate and collide to the sample, and they create several kinds of excitations. And one interesting aspect is that you can really excite like everything. And we could observe then again the 2.1 line here, and some phonon replicas were also present, and also some phonon replicas and emission close to the 300 nanometers, where it is the 4.1 emission that we could also observe in other data that I'm not showing here. So with this, I'm reaching my conclusion. So I presented you 2 works in which I tried to correlate electronic, morphological, and optical properties. So on the first case, we could see the presence of defects on the sample and see that the sample is p-doped as a consequence of these defects. And we could see that since it's p-doped, the luminescence is basically triggered by the injection of electrons on this system, in the case of the tungsten selenide. And in the case of hexagonal mononitride, we could determine the electronic band gap on the defect-free sample. And associating that with the excitonic emission, we could determine the exciton binding energy, which is a very important property of this material, and which explains a little bit of why it has such a high optical emission, even at room temperature. And we could also see the first data on these defects, which are very, very interesting because they can act as this source of single photons. And with that, my main point is that from a more broader perspective, we think that the STM associated with some light emitting capabilities is really a great platform to study on the same sample and possibly on the same region of the sample morphological, electronic, and light emission properties of several kinds of nano-objects, including 2D materials and its defects, but also nanoparticles and other systems that can be of interest. And with that, I'd like to thank you for your attention, and please you can access my website and see a little bit of what we are doing and next studies that we are pursuing.
Thanks, Luis, for that riveting presentation. There's still some time left in the webcast for some questions. So let me just read off a few, and you can take them one at a time, Luis. So the first one has to do with your discussion of the water layer under the tungsten selenide. Can you provide further evidence of the presence of that water layer under the monolayer of tungsten selenide?
Yeah, sure. So I just put it back. So there are just 2 questions related to this layer. First, is it there or not, and is it water or not, right? So we have made several, not only those that I presented here, but replicas of the samples, and we could always see that before this thermal annealing, the step height is always bigger. So sometimes it is even bigger than the value that I have shown here. And after the annealing, you always see that the sample like collapses towards the support. And I also saw this Raman, that is a very strong evidence that the sample is not coupled and is really coupled to the gold support afterwards. But I think that the most relevant or widespread evidence comes from the literature, because there are several studies that have really aimed to make transfers in wet environments and have shown that the moisture in the air really is on several kinds of surfaces. In particular, this kind of gold that we used is known to be hydrophilic. And then we transfer this sheeting material on top. This water has simply nowhere to go, so it really remains trapped. And several studies could show that if you do, for instance, photoluminescence mapping, and you see that this water on the close to the border of the TMD starts to get out first, and you see that the border of the TMD starts to get different optical properties as seen by photoluminescence mapping. So, of course, it would be interesting to look in deeper and have a spectroscopic signature of the water, but water is really the best the best suspect, because it's really present in all these kinds of surfaces since they are prepared in ambient conditions.
Well, you mentioned there are other effects. There's another question related to tungsten selenide. It says, do you see any moire effect on gold after the water has been desorbed?
Okay, so the moire effect is really linked to the existence of two similar patterns, like the TMD in one side, or the HBN, and its underlying support, which should have some similar ordering. But the gold we used here, it was not a reconstructed single crystal. That would be hard to preserve the reconstruction in air for the transfer. So it's just I sputtered polycrystalline gold, so it didn't. It doesn't have sufficiently long-range order to impose a pattern to the TMD on top and to present this moire pattern. But of course, it would be possible to see this pattern if the substrate had the same kind of ordering as the layer on top.
Here's another question. You show cathodoluminescence on the hexagonal boron nitride up to 300 nanometers and not to shorter wavelengths. Why is there no band-to-band emission?
So that's a very good question. I just put the slide so that everyone has in mind. So question is why we cannot keep going to shorter wavelengths up to the point that we can see the 6.1 EV emission. So it should be there, and we have some luminescence at shorter wavelength. But to look at a spectrum that is so large like this one, we are always obliged to make a correction of transmittance of every single optical element. And we have done that in this case, and we had a lamp that can only correct from 300 to like 900 nanometers. So this spectrum has been corrected, and I didn't want to explore the other bits below 300 that were uncorrected. And in this particular case, there was no light emission at 6 EV or 6.1, and we think that is because some of the optical elements that we have used were not transmitting light, were not suitable for this range. So it's a matter of getting the optics really optimized for the DUV such that we can reach this wavelength range.
And here's another question about the light collection efficiency. You said that your device has about 70% collection efficiency. How was that efficiency determined?
So there's basically two ways that we can determine that. It's not something that is easy indeed. From the modeling point of view, we can model the mirror and the optics that we have to think on the paper what should be the light collection efficiency, supposing that everything is working as it should. So this is what gives the number of 72%, but there's always a question of how reliable this number is. But one way to check this number is to get a standard sample and to see what's the count rate that we get, because a standard sample has a known light emission efficiency. And for that, we used the gold 111 surface. I have no slides to show you regarding this matter, but in this sample, we had a known tunneling current and a given count rate. And if we correct this count rate, this photon count rate, to the amount of photons that were emitted by the sample, we get the quantum efficiency of this gold surface, and we could really get the same number as on the literature. So we think that within a few percent, we should be correct in our collection efficiency, because otherwise our quantum yield of the gold surface would be offset with respect to the literature. So we have, in one hand, the modeling of the system, and on the other hand, this is standard sample that shows us that it's emitting, that we are collecting as much light as we think we are.
Well, as I look at the clock, I notice that we're coming up on the top of the hour. So maybe that's a good place to end the presentation. Thank you, Louise, again for a fascinating view of the subject. And everyone, thanks for joining us. This concludes today's webinar.
Thank you.